I'm Jyoti Sharma, and I will start the live session from 6 to 8 p.m. And this is week 3. And the live session will be for the course Climate Change Extreme Event. So, this is my brief introduction that right now I'm final year PhD student. Uh, Yeah. Okay. So right now I'm a PhD student from ISER, Bhopal, and I already have cleared UGC NET GRF and ICR NET. And right now I'm a PMRF research fellow. That's why I have responsibility to teach you online for 2 hours every week. I already have past experience related to the teaching on NPTEL. The courses has been listed in my presentation, and I think that will help me to teach you in a better way. Okay. This I already have told you that I have a lot of MCQ questions. Sometimes it is a multiple choice question, and sometimes it is multiple select question. And with the discussion, I want you to give the answer. And if you will have any doubt, then I'm here to solve your query. So that's why your participation is highly valued. Okay, so coming to the syllabus and the lecture that we already have covered. So because this is week 3, we already have covered the lecture from lecture 1 to lecture 12. And this time we will have question from lecture 9 to lecture 12. So till now we have covered what's the difference between weather and climate. Then what do you mean by climate change? What do you mean by climate extreme? And we took some example of climate extreme, for example heat wave and cold wave, precipitation extremes. Within precipitation extreme, we talked about extreme rainfall and drought condition, and we also took the case of tropical cyclone. With these example of the climate extreme, now if we want to see such kind of extreme cases, we should have data first. Okay, so we have multiple climate data source that we will talk about today. And we will talk about what kind of data we can have from these sources. Then even if we will have some data, then there may be some error in that data set. So how we can reduce that error, how we can handle the gaps, how we can handle the temporal biases, so that we will try to cover today using multiple select question and multiple choice question. And very important part is the introduction to climate model. What do you mean by climate model? The first thing. The second thing is, if we have observational data set, then what is the need for the climate model? Even I will show you climate model that I have, that I use, the type, resolution, and what application we have for this climate model, and the summary part. uh, Before going to the multiple select question, the one question was asked by Alice. So this is, may I ask whether the recording will be available for reference and watching later? Yeah. On NPTEL website only, there will be a link to the Excel sheet. In that Excel sheet, for each week there is a video link, so you can go and you can watch anytime whenever you want. So yeah, it will be available even after this default time 6 to 8 p.m, so you can watch anytime. Okay, so now we are moving to the climate data sources from where we can get the data, what different type of data we have, and even I will show you different data format that we people use. Okay, so please keep in mind these are MSQ, that is multiple select question. We may have right option more than one. So you need to tell me which are the right options. So my first question is, which instruments can provide information about atmosphere above the surface? And I have 5 options: radio sondes, ocean buoys, a satellite sensor, rain gauzes, and weather radar. So I encourage you to please write in the chat box so that I can learn what information and what knowledge you have, and um, what level of effort I should put into. So this is your surface, and this is, let's say, your atmosphere. So I'm giving you the example of atmosphere. Let's say it is your troposphere, and troposphere is, let's say, this is 0 kilometer. So we are at, let's say, sea level height, and this is 13 or 17 kilometer height. So if we want the information, if we want the climate information of this atmosphere from 0 to 17 kilometers, so what kind of instruments we can use? Do you have any idea? Okay, so I got one answer, so can I expect more answer from the audience? So these first 20 questions are similar to your assignment questions. So I think these first 20 questions will help you to solve the assignment that you need to submit by 12th of August or 13th of August. I don't remember the date exactly, but yeah, these questions are similar but not same, same to the assignment questions that has been given for week 3. Okay. Let me explain you. The one person, LS gave me right options that are A, C, and A. Let me explain you what are these. Okay, radius only. Radius only is a kind of balloon that we use. So what we do is, uh, if there is some observatory, within that observatory we have some balloon, and so in which we have gases, for example nitrogen or helium, that we fill in the balloon, and then we drop this balloon into the atmosphere, right? But within that balloon we have some sensor attached here. So we have sensor, that sensor may be related to the temperature, so we may have some thermometer or something related to the wind, related to the relative humidity. So we do attach a lot of sensor to this balloon, and then we drop this balloon to the atmosphere. This balloon will go up to, let's say, 6 or 7 kilometer, or even up to 10 kilometer up. So what we can get is, let's say this is your height and this is temperature. So what we can get is that along with height, whatever temperature we have. So such kind of graph we can get out of the sensors. That sensors are giving me the information that are attached to the radio sonde. So radio sonde is nothing, these are the balloons, and we attach a lot of sensor to this balloon, and we drop this balloon to the atmosphere, and that's how this balloon will go to the top, and whenever it will go to the top, it is taking the information at each height, right? And so in real time we can monitor the temperature, relative humidity, and a lot of variables. We can see the changing with the height, and that's how this is important for us. So the first is radio sunday. The second is ocean bios. So these are the sensors that we have. I will show you in the next slide. There is a one picture. So this is something, the sensors that we have, that we keep it in the ocean, and we drive it, and that's how this sometimes this is automatic, and this will go beyond from 1 kilometer to another and to the thousands of kilometer, and that's how we are getting information related to the ocean. So there will be, at the depth we will again attach some sensor to this bios, and that's how we will get some information. Satellite sensors, you already know that satellite is giving us a lot of information related to the surface and even related to the atmosphere. So for example, um, some satellite sensor can give you the information about greenhouse gases or even different gases that we have at each particular height. So this is how satellite sensors can help you to get the information about the atmosphere that is above the surface. Rain gauges is for the surface because this is giving the information of your intensity of precipitation, or you can say rainfall that we have, but it is giving the information how much rainfall we got on the surface. So that's why this is not the right answer. Weather radar is again a lot of sensor that we attach. It may be that it is the coverage of the radar is, let's say, 30 kilometer or 40 kilometer, sometime it is 200 kilometer, and that's how it can give you the information about that particular spatial extent. So this is again the one sensor or instrument that will give you information about the atmosphere. If you have any question related to that, please let me know. Okay, so this is Radio Sunday. If you will go to any observatory, a meteorological observatory, then you will see most of the time we drop such kind of balloon, and we have here some sensor attached to it, and here some sensor attached to it. So that's how we get vertical profiling of the atmosphere using this Radio Sunday. But yeah, it is expensive, and sometime the thing is, we have to drop this balloon every day in the same time. Otherwise, there will be some error that we can encounter. So then there may be some manual error, but we have to ensure that we are dropping it in the same time. This is ocean bios, and here there are some sensor which is giving the information, and here also some sensor that are having the information at the depth of the ocean. And this is your weather radar, and this is giving some light or rays, and that's how, and then how much reflectance it will get, and based on that it is giving us the information of your atmosphere. So we have different instrument by which we can have a lot of climate related data set. Okay, now we are talking more about the satellite. We do have different type of satellite. The one is passive remote sensing, and one is active remote sensing. I will tell you what's the difference between these two. So the question is related to passive remote sensing. So which statements correctly describe passive remote sensing? And I have again five options. It detects naturally available radiation. It always sends microwave pulse toward Earth. Visual imagery can be passive. Thermal infrared sensing can be passive. Radar is a passive technique. If some people are not aware of remote sensing or satellite, you can just drop in the chat box, and I can explain everything, whatever you want to learn about this, so that we are on the same page. You are learning the same thing that I'm trying to teach you. So which statement correctly describe passive remote sensing? Yeah, so again I got response from Alice, and that is um let me see. Okay, he told me ACE. Okay, let me tell you. Okay, so the right options will be ACD, and I will explain you why it is. Uh, yeah, Sanika, this is ACD. ACD. Yeah. So let me explain you first what it is exactly. So let's say this is your Earth, and here you have satellite, right? So, remote sensing means you are getting some information, you are sensing something, you are getting some information from the distance. So, remote means you are taking some information from the distance. So, you are not touching. So, this satellite is not touching the earth, but still it is getting a lot of information about the earth. So, such kind of techniques are known as remote sensing. The one example is the sensors. So satellite have a lot of sensors, right? That sensor are sensing the reflectance of your earth, and that's how this is the one technique of remote sensing. The another is photography. You always take picture, right? And picture may have some information. So for example, you are taking the picture of soil, or you are taking the picture of a one person, or even you are taking the picture of one human organ, and from seeing that picture you are getting some information, right? So getting that picture is again the remote sensing thing. Okay, because you are sensing, you are getting some information from the distance. So this is remote sensing, and satellite sensors are the part of remote sensing, the first thing. The second thing is, what is the principle of remote sensing or satellite? So again, let's say this is your earth and this is your satellite. Satellite will move, right? Will move, or your earth will move, and this will be kind of stationary. So you can say geostationary. The speed of your satellite and speed of the rotation of earth may be same, and that's why uh, it will be look like that your satellite is fixed at one position, because um, your earth is also rotating with the same speed. With the speed, satellite is also moving, right? This is known as geostationary satellite. So now what will happen? So it has some sensor. So let's say this is one sensor that satellite have. Okay, so what it will sense? We have sunlight, right? We have sunlight, and you know that. And this sunlight will be in short wave radiation. Okay, so sun is giving us the sunlight in the form of short wave radiation. What will happen? It will reflect. Whenever it will strike to the surface, it will reflect, and it will be changed into long wave radiation. Okay, so this reflected light will be sensed by this sensor, and based on the reflectance, there is a one very important terminology in the remote sensing, that is reflectance. Based on the reflectance value, the sensor will tell a lot of information. For example, on your earth you have water, right? You have building, you have, let's say, forest. Okay, on each part there is a short wave radiation coming, and then there will be reflected light. But because the surface has different property, then this long wave radiation will also have different property, and that different property will be sensed using this reflectance by the sensors. And that's how we get a lot of information about the surface of your earth, right? So that's how remote sensing work. This is the remote sensing thing. Now coming to two things. The one is active remote sensing, and the second is passive remote sensing. As I told you, we have satellite and we have here earth. Sun is giving some radiation, and then it will be reflected and it will be sensed by the sensor that we have on the satellite. So this is known as passive passive remote sensing, because the energy is not given by the sensor, energy is given by the sun only, right? So the rays are given by the sun to the earth, then these rays will be reflected and it will be sensed by the sensor. This is your passive remote sensing. Active remote sensing is sometime, for example, in the night time we don't have sun rays, then how we will get some information about the reflectance? Then in that case there is the active remote sensing. What will happen, the sensor itself will give rays, okay, will itself will give some radiation, and then there will be the reflectance. So when sensor itself is giving the radiation to the surface and then it will be reflected, this will be the part of your active remote sensing. It means we are giving energy by ourselves. In passive means sun is giving the energy, whatever reflectance we will have, we will the satellite will sense that reflectance. Okay, this is your passive remote sensing. Now what is the need? First I told you, in the night time, let's say we don't have sufficient radiation, then and if we want the information in the night time, so sometime we need active remote sensing, right? The second thing is, sometime let's say we have clouds here and we have earth here, and this is your sun, and your sun is giving short wave radiation, but it will be reflected back by that cloud only, so we are not getting information about the earth. So that's why sometimes satellite itself has to give radiation that can penetrate into the cloud and that can reach to the earth. And that's how active remote sensing can give you the data even when there is a cloud, because in the case of cloud, your sunlight is not enough because sunlight may be reflected back, but we will give some radiation by satellite itself which will penetrate into the cloud and will reach to the surface, and that's how this is your active remote sensing. So now coming to the options that we have about your passive remote sensing. It detects naturally available radiation. As I told you, sun is giving the radiation and that will be sensed by the sensor. That is the passive remote sensing. So this is your correct information. The second is, it always send microwave pulse toward earth. No, if we are sending microwave pulse from the sensor, then this will be your active remote sensing, right? This is not the passive one. So this is your wrong statement. Visible imagery can be passive. Yes, it can be passive. Why? Because sunlight is mostly in the form of visible radiation and infrared, right? So if you will see the wavelength of your sunlight, most of the wavelength will lie into this visible and thermal infrared sensing. So these two options are also correct, that visible and this thermal infrared. Thermal infrared will be whenever it will strike to the earth, it will convert into thermal infrared. So this is again can be passive. Radar is active because in radar we send the pulse from sensor, and then this pulse will be reflected back, and then we will sense that reflected back radiation, and that's how this is again the example of active remote sensing. Radar is the part of active remote sensing but not the passive, and that's why A, C, D are only the right option, not B and E. If you have any doubt, you can just let me know. Otherwise, we can go for next question. Okay. So this is exactly the picture that I tried to explain. Passive is sun itself is giving the radiation, and that will be reflected radiation will be sensed by the sensor. And active is your satellite itself is giving the radiation, and then that radiation will be reflected and sensed by the sensors that we have on board the satellite. Okay. The next is, which factors can limit satellite based climate observation? It is satellite data are not the perfect one. There may be a lot of reasoning why the satellite data is not the perfect as the observational data set. And you have a lot of options here: retrieval uncertainty, cloud contamination for some sensors, requirement for ground calibration, perfect accuracy over all surfaces, differences in sensor characteristics. Which factors can limit satellite based climate observation? As I told you, um, okay, I'm getting the answer, so let them give the answer first. Okay, I got answer from Sanika, and this is A, B, C, E. Can I expect more answer from more people? Yeah. So I got response that is A, B, C, E, and that is the right one. And let me tell you why. Again, we are talking about the Earth and satellite we have, and in that satellite we have sensor, and what we are saying is that sun is giving some radiation will be reflected, and this reflected radiation will be sensed by our sensor, and that's why we are getting some information. Okay, the thing is that we are getting the reflectance. The only variable that we are getting is reflectance, but with that reflectance we may get information about temperature, we may get information about humidity, we may get information about cloud cover, we may get information about different gases. So how this is possible? It means uh, we are having a lot of equations, we are putting a reflectance value in that equations, and with some calculations these are giving us different climate variable values. Okay, so for example, if we are multiplying a reflectance value with something, let's say zero point 0.5, I'm just giving you one example. And if multiplication of reflectance with zero point 0.5, it may be that this is giving you the temperature value in, let's say, Kelvin. Or we may divide something, we may add something with this reflectance value, and even we have to do the logarithm of this. So this is how we are putting a reflectance value in different formulas, different equations, and that's why we are getting different climate variables out of this reflectance value. So retrieval is nothing but how we are getting the information of climate variable from this reflectance. It may be that your formula have some errors. Okay, it is just giving us the reflectance, and it it may or may not be that that formula is giving you the exact value of your climate variable, let's say temperature, because it is not directly uh, sensing the temperature. It is not the thermometer, it is just the reflectance, and based on reflectance we are calculating the temperature. So this is known as the retrieval. So we may have some retrieval uncertainties because we are just calculating the reflectance, the first thing. So yeah, this can limit satellite based climate observation. The second is cloud contamination for some sensor. As I told you, if we have cloud, then reflectance value will vary, and that can mislead us. And that's why cloud contamination can also give you some limitation for this satellite based climate observation. Requirement for ground calibration. As I told you, we have some formulas, right? Uh, we have for one so let's say for the temperature calculations only, it is not just one formula that we have, in which we are putting the reflectance and we are getting the temperature. We may have thousands of formulas, okay, different formula, based on that we are getting the temperature. So we need to tune that formula, and that's why we need ground calibration. So how, from reflectance we are getting the temperature, we need some tuning into that formula, and that's what is it, it is requirement for ground calibration. Okay, perfect accuracy over all surfaces, no. Sometime, for example, if it is a one is scattered forest and another is dense forest. Dense forest may have less accuracy because sometimes it can't penetrate to the ground because we have multi-story of canopy in the forest, in the dense forest. So that's how, at different surfaces we may have different type of errors. Okay, so it is not that we will get perfect accuracy over all surfaces. Differences in sensor characteristics. So we may have different sensor on board over the satellite, and different sensor may have different characteristics, and that's why uh, different sensor can give you some bias errors. Okay, so that's why A, B, C, E are the right option, but not D. If you have any doubt related to this question, you can just let me know. Otherwise, we are moving forward for the next question. This I already have explained to you. The retrieval uncertainty means satellite usually measure radiance, and then we infer variables such as temperature or gas concentration. So retrieval process may introduce some uncertainty. Cloud, I already have talked about that it can block or it can distort your observation, especially visible and thermal infrared sensor. We need ground calibration because satellite products often need comparison for the calibration and for the validation part. Then different sensor may have different characteristics, and that's why we need the consistency between the data sets, and that can also create some error. Okay, the next question is related to the ocean bios. Which variables are commonly observed using ocean bios? And we have salinity, ocean current, wave height, sea temperature, atmospheric ozone profiles. What we can observe using the instrument which is known as ocean bios. So if we are putting some instrument in the ocean, then it means it will give some information about the ocean, right? So we are putting some sensor in such a way that it can give as much as possible variables which are related to the ocean. So I think this is the simpler one to answer. Uh, any suggestion, any option? B and C are the right one, but along with that, we have more options that are right. Okay, so yeah, so the right options are A, B, C, D. That are salinity, ocean current, wave height, and sea temperature. It means we initially in the ocean bios we had less sensor, but right now we are having a lot of sensors that are giving us the lot of information about the ocean. For example, it can talk about the salinity. It can give you the information about the ocean current, because we are putting sensor at the depth of the ocean also. We are getting information about the wave height and sea temperature also. If we are talking about atmospheric ozone profile, then we do have satellite sensors that can give you the information about atmospheric ozone profile, but not the sensor which are attached to the ocean bios. Okay, now the question is, which approaches can improve confidence in climate observation? Combining independent data sources, cross validating satellite and ground data, ignoring systematic disagreement, using regional observing network, checking long term consistency. How you can improve the confidence in climate observation? Just speak up. Even if you are giving the wrong answer, you will learn something, because I will explain that option, why it is wrong, why it is right. So I think that will help you to learn more. So I encourage you to please respond in the chat box, so that this can be a two-way learning process. Okay, so I got some responses, and yeah, except C, the answers are A, B, D, E. Let me explain you how. Okay, first, the thing is, if we want climate data set, right? If I want climate data set, for example, let me make it simpler for you. If I want temperature data set, so from where I can get this? Can you tell me what are different way by which I can get the temperature value? Let's say we have one forest, and we had forest, let's say in 2000, and by 2020 the forest has been cut down, and it is now the agricultural area. And now we want to see that what temperature responses that we are having after this land cover change. So we want climate data or temperature data from 2000 to 2020. So how this climate or temperature data is changing with the time when we are cutting the forest. Okay, so how you can get the data of the temperature? Can you tell me how we can get the temperature data? The one is, in that forest area we are inserting some sensor, right? So this will be known as your ground based data set. This is your ground based data set. What more, how we can get the data of temperature for that forest and then to agricultural area? Sometime for the research purpose we insert the thermometer and a lot of sensor in that particular study site, and that what will be covered under this ground based observation. We may have different ways by which we can collect the temperature data set. What are the different ways? Can you tell me more options how we can collect the temperature data set? Can we get it from satellite also? Satellite is also can give us daily or even monthly, even hourly data set for the temperature. Okay, so satellite will also give you the temperature data set. What, how we can get more information about the temperature? Now the thing is, if we want to see that what will happen in 2050, ground based data we are already getting from the sensor that we put into the forest study site. Then we can get the data from the satellite also. If we want to know what will happen in the future, how the temperature will change, so we can also take the help of climate models. I will tell you what are these climate models in detail that we use, and these climate models can give you the data for next thousand of years, and in the past also it can give us the data. Okay, so what we learned is that we can get data from ground, that we are putting sensor there. We can we can get the information from remote sensing. Example is satellite. From satellite we can take the data. And third is from climate model. Okay, the thing is, sometime, let's say if it is a cloudy season, and let's say if we gave the duty to one person to collect the temperature data set, but if that person is sick or something happened to that person, and that person is not performing his duty properly, then what will happen? It may be that for few days he is not taking that data set, or sometime our uh, sensor is not working on the ground. There may be some default in the sensor, and that's why it may be that for 10 days we are not getting any information about the temperature from the ground based sensor. It may happen. Okay, again I told you satellite is based on the reflectance. It may also have some errors. Climate models are based on your mathematical equations that we know about our atmosphere, about earth, and we try to solve some partial differential equation, and based on that we can tell, okay, this will be temperature in future if this is the case. Okay, so the thing is, we have ground based, we have satellite, and we have climate model. But these three type of sources may have some errors, and that's why the best product will be when we are merging these three information together. So for example, if we have ground based data set and we have satellite data set, if there is some error in the ground based data set, we are filling with the satellite data set, and even with the help of the climate models. And that's how we are having the perfect blend of data set that we can use for the temperature, which is known as reanalysis data set. Reanalysis. So reanalysis data set is the blend of ground based, satellite, and even the climate model. So for our research purpose, most of the time we people are using this reanalysis data set, because we are considering this data set the best one, because this is the combination of all the data set. Okay, so how we can improve the confidence in the climate observation, how we can improve when we are blending, when we are combining all such kind of data set that are available, either it is satellite based or climate model based, or it is ground based. If we are combining, and then we can have improved confidence. And that what the question was. Combining independent data sources, as I told you, cross validating satellite and ground data. So as I told you, satellite may give you some error because it is based on the reflectance value. So if we are comparing it with the observation, then there we can correct the satellite data set, right? So this is how we can improve the confidence. Then using regional observation observing network. Satellite have coarser resolution. Satellite can give you the mean, but if we want the value at particular region, then we should have the networking of your sensors there. So that's how using regional observing network. Checking long term consistency, it is very important that there should not be outliers, there should not be if we are using one sensor, then the sensor should not be changed. So this is the consistency that we have to maintain to get the correct, confident, improved data set, right? So what we learned from it is that we have reanalysis data set that right now we are using for our research purposes. Can you tell me some organizations which are giving the reanalysis data set? You can download it anytime. Can you name some reanalysis product? Okay. Before that, what we talked about is the observational data set. Can you give me the example of observational data set? For example, IMD, Indian Meteorological Department, having a lot of sensor across the India, and that is giving you the temperature data set. So IMD is giving the temperature data set, which will be known as the observational data set. So IMD data set is the one example of observational data set. Now, if I'm saying that, can I know the name of some reanalysis data set? Can you tell me the name? Have you heard about ERA 5? ERA 5 is the one of product. Have you heard about Terra Climate? So these are some different agencies are giving different product for temperature, let's say itself, which are combining satellite observation and even the climate models, and these are giving the data set across the world and kind of considered the best. But some are giving high resolution data set, some are giving very coarser and blur data set, right? So that's why based on our need, we can use different data set. If you need finer resolution, that you can rely on this Terra Climate data set. If you want 25 kilometer spatial resolution, then you can rely on this ERA 5. Terra Climate is mostly giving you the monthly data set, right? But ERA 5 is giving, it can give you hourly, daily, and monthly also. So most of the time we people use ERA 5 one. Okay, so let me show you some of the data set because it is important to let you know about this data set. Mhm. Okay, so if you can see my screen, so this is your ERA 5 data set. So what I'm saying is, yeah. So if I'm writing here ERA 5 reanalysis data monthly, and so climate, this is your Copernicus. So this is the Copernicus website. This is giving you a lot of variables. So ERA 5 monthly average data on single level from 1940 to present. So it can give you a lot of variable data set from 1940. If we so here, if you will see, ERA 5 is your fifth generation ECMRWF reanalysis. So this is a reanalysis data set for the global climate and weather for the past 8 decades, and the data is available 1940 onward. So from here you can download the data set. So let's say I'm going to the download. So here you have a lot of variable. Let's say I'm going to the 2 meter temperature that we want. So I will select 2 meter temperature. These are different variables. So for which year you want the data set? So let's say I want the data set for 2025. For which month you want the data? Let's say I want data for January only. And within January, so this is hourly data set. For which hour you want the data? So let's say I want data for 6 a.m. And Do I need that data for world or for the some particular region? So can you tell me the region, Indian region? So for the north it is, let's say, 40, for south it is 6, for west this is something 60, and for this is 100. So we are cutting the data set for India. And then, okay, now the thing is how you want the data. So if we are getting data for India, so it will not be just one value. It, for each grid it will have some value, and for each time period it will have some value. So the climate data is multi-dimensional data set that we have to download. So most of the time we have one format, that is netcdf.nc dataset that we use. So the data set most of the time we use is netcdf, and that's how we can download here. After login, we can submit a request, and then we can have data set from this era 5, and from 1940 you can have the climate data set, and based on your interest you can do some analysis, right? So this is the one reanalysis data set. Then the second one is terra 1. So let's say if I'm just searching the Terra climate, so there is one website which is giving. So again, you see, Terra climate is the data set of monthly climate and climatic water balance. For this, it is giving you the data for the resolution that is 4 kilometer. The resolution is 4 kilometer, and it is again reanalysis data set. So what it is? So can you see here? Uh, it is merging. It is also using era 5 dataset. Also it is using world climate dataset. So it is combining all datasets so that it can give you the better one. So that's why this is again your reanalysis data set. And again you will go to download. Let's say you want to download for individual year. Can you see .nc? So .nc is your netcdf format. Again we are getting data set of the climate, which is again will be in file format, that is .nc. So that is netcdf. So this is how these are the reanalysis data set. Then the one I told you that we can also use the data from climate models. So if you have heard about CMIP6 dataset, so these are giving you the data for the future. So how your temperature will change in the future, how your precipitation or rainfall will change in the future. So that also you can download from CMIP6 climate projection. So these are SSPs based on some scenarios. You can have the future data set. So let's say I want the air temperature data set. We have different okay, at what level of your atmosphere you want the data. Either you want data at the surface. So this is 1000 hpas at the surface. If you are going up, then a different level of your atmosphere you can have the data. Then we have a lot of climate models. So for India, IITM, that is Indian Institute of Tropical Meteorology, have one Earth System Model (ESM) for which we can have the data. So let's say I'm selecting IITM ESM model, and again there will be year for which year I want the data, and then for month, for region, and then we can send the request, and that's how we can download the data set in .nc format. So and we people use such kind of data set for the research purpose. So let me again show you some data set, if it will work. So can you see I have a lot of files. The format of this file are .nc. I will show you what kind of data set it is. I'm just copying some data path. So this is how I'm going to this path that I already have. Can you see I already have IMD dataset? Let's say I have ERA 5 dataset. I have CMIP 6 dataset. So let me show you. Your Indian Meteorological Department is giving the data for temperature and also for the precipitation. So how this NC or net CDF file format look like? So let me show you about this file. Mm, okay. For example, I want to see 2 meter temperature, and I have data from 1980 to 2014, and this is monthly data set. So let me show you this data set, how it will look like. It is taking little time. Yeah. Okay. So this is how this is the data set you have for January, and this is for 1980. So we have different grids, and for each grid we have data that is given by the IMD. If we are moving this one, um, so this is how every month your temperature data is changing. Okay, so can you see how much values we can have if we are extracting into the Excel file? So that's why this file is NC, and we do some computational thing on such kind of files only, and based on that we can calculate the extreme climate change events, or if you want to see how the drought is happening over the India, the tropical cyclone, heat wave. So we can calculate using such kind of data sets. Likewise, likewise, I also have precipitation data set. Then ARA 5 will be same like IMD, and if you will see CMIP 6 dataset, then the resolution will be very coarser, and that's how we can download different reanalysis and climate model based dataset, and we can use it as per our area of interest, right? So let me go back again to yeah. Okay, so I think you got little idea how we people work on climate data set. So it can be observational. For example, IMD is giving you the observational data set. We may have reanalysis data set. For example, ERA 5 is giving you the reanalysis one. Climate model may also give you data set even for the future and even for the past or historical. And for example, CMIP 6 I showed you. So this is how we can have different type of data, but each data may have some error, may have some biasness that we need to remove. So we have to do a lot of pre-processing before using that data set. If you have any question, just let me know. Otherwise, we are going to the next question. Okay, now the next question is, which situations may produce missing climate data? Instrument failure, communication loss, complete data transmission, sensor malfunction, interrupted observations. I think now you can give me the right answer quickly for this question, because now you already know what are the challenges while collecting the climate data set. Um, yeah. Yeah. So Yes, except C, all the answers will be right. Instrument failure, as I told you, if some sensor is not working, then what will happen? Or if some instrument, let's say if we have thermometer, and if that thermometer is not working properly, then what will happen? So the instrument failure may produce missing climate data. So for example, I gave you the example of forest, right? If we are inserting some sensor or thermometer there, and that thermometer stop working, then what will happen? It will there will be the gap for, let's say, for 10 days or 15 days, that we are not getting the temperature data set. So this is known as the instrument failure. We may have communication loss. So satellite is giving us the data set, and the old data set that the satellite is giving us on our computer in SAC, you have application center, right? So if the communication, if there is a communication loss, it may be that sensor is not giving the data to the station or to some centers where the satellite is giving the signal. So if satellite is not giving the signal and we are not getting the information, then this is again may produce missing climate data. Then sensor malfunction, again I told you, if sensor is not working properly, then again interrupted observation. This may be due to instrument failure, maybe due to manpower. If some person is sick, then it may be that he is not going there and he is not collecting that data set. Until or unless the data is automatically stored, that we may have missing climate data if it is dependent on the human. So that's how we may have a lot of missing climate data, and we have to deal with this missing climate data. Okay. Now the question is, which methods may be appropriate for identifying erroneous climate observation? Now the options that we have are outlier analysis, data validation, visual inspection, random deletion, comparison with nearby observations. Okay, I get, please share the direct link to the web page where the recording of this session can be found. Yeah, I will share the link. Actually, uh, these recordings are uploaded on YouTube, and so I can give you the YouTube link, so that whenever it will be uploaded, then you can see. Um, Along with that, always on NPTL, Excel sheet is you can find Excel sheet where you will get the link for each videos. But yeah, I will give you the link also. No worries. Okay, let me see the answers. So this is A, B, C, E that I'm getting. Yeah. So except D, all the answers are correct. Okay, so how we can identify that whatever data we have, that data have some default, and that some data have some error. So how we can get this? If we have outlier analysis, so for example, we had all the data. So for example, for the temperature, for the winter time, the temperature for Delhi, let's say, if it is near to 15 degrees Celsius, but for one day, let's say we got 40 degrees Celsius. So this is kind of outlier. So if all values are near to 15 degrees Celsius, and if we are getting 40 degrees Celsius somewhere, then we may have some doubt how we got to 40 degrees Celsius. It may be due to some error, or it may be due to some climate extremes. Okay, so, and this is your outlier, right? 40 degrees Celsius is your outlier, because mean or median is near to 15 degree Celsius. So we can identify the outliers, and we can remove such outliers, so that we can correct some climate observation. But sometime removing the outliers may be wrong for us, because it may be that this 40 degrees Celsius is the true value, it is not the error value. It may be there is some climate extreme happened over Delhi and we got 40-degree even in the winter. It may happen, it is possible. So if we are removing this outlier, we may get misinformation. Okay. But most of the time, we are not having this. So if we are removing this outlier, and that's how we can also sometimes fix our climate observational data set. So the one is outlier analysis we can do. The second is data validation. So for example, satellite is giving you uh, 40 degrees Celsius. Okay, but the observational data set, you may have a lot of sensor in Delhi, and that Delhi sensor are saying, no, 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 this is not 40 degrees Celsius that you calculated from your satellite. This is 15 degree. So this will be you're validating. Sometime satellite may be wrong. Okay, satellite may give you the wrong information. So what we have to do is we have to validate it with the ground-based data set. We have a lot of sensor on the ground, and we can see the difference between these two, and we can see the data validation. So data validation is also one method by which we can identify if there is some error or not. Visual inspection, as I showed you right now, the IMD or ERA 5 data set. So after seeing that visual map also, you can get some information where your data set has error or not. So visual inspection may also help. Then random deletion is not the right way to identify. Comparison with nearby observation, as I told you. If one sensor is giving wrong data, then we can go to some different agencies that are having the data set nearby, and then we can compare these two. Okay, now the thing is, if we have data and data may have some error or something like that, and if we want to pre-process it before using it, then which are the processes that are belong to typical climate data pre-processing workflow? I have 5 options here: data cleaning, normalization, transformation, aggregation, and parameterization, atmospheric convection. If we want to pre-process the data before using it for some other purpose, then what are these processes that we have under this pre-processing workflow? I got a response from Sanika and Alice. Okay. So yeah, except E, the answer are A, B, C, D. Let me tell you how. So again, let me see that this is your Delhi area, okay, and we are dividing this Delhi area into, let's say, these are 16 grids, okay. So we are having the picture, or let's say climate data or something. So if we are getting the climate map of Delhi and we are dividing Delhi into 16 grids, it may be that this grid doesn't have any value. The value is missing for this grid, or let's say for this grid. Okay, so this may happen. So what we have to do is, there is the one technique, interpolation. So based on the values that we have nearby, we can fill this grid with some value from nearby with different methods. Okay, and there may be nearest neighbor method, this may be linear method, this may be spline method, this may be IDW. So we have different statistical method by which we can fill it. Okay, the first thing. uh, the second is, if so this is your gap filling. The second is, it may be that this grid have value, but this value is wrong. This value is wrong. Then what you have to do is, you have to remove this grid. Either you will remove this grid, or you will fill the value from the near grids. You have to correct your climate data. So first, for this, you have to clean your data. In last question only, it was like that. If you are having outlier analysis, and what if we are out of this 16 grid, if this grid is giving you the outlier value, then we can remove this grid and we can do the analysis with the remaining 15 grids. Okay, so this is how we can clean our data set. Okay, the first thing. The second thing is normalization. What do you mean by normalization? um, Let me remove this. Normalization is, for example, you want to see, this is your temperature data set, and this is your let's say relative humidity temperature relative humidity data set, and this is your time. Okay, temperature is giving some data set like this. Relative humidity may also give data like this. Okay, it is possible, but the thing is that relative humidity unit is different and temperature unit is different, so we can't plot them using same single y-axis. So what we do is, we normalize our data so that whatever value we have of the temperature, that value we can have from 0 to 1, let's say. And for relative humidity also, we can have value from 0 to 1. And then we are plotting. So this is 0 and this is up to 1. Then we can plot and we can see the pattern, how your temperature is changing with the relative humidity. This is how we do the normalization. We will give some range in which both these variable will lie, let's say from 0 to 1 or -1 to 1. So in that way, we do normalize so that we can compare one variable to the another, and we can remove the unit out of these all variables. So this is how we do the normalization. The third is transformation. So how transformation? So for example, uh, you have a precipitation data set or rainfall data set, and this is again time, and we are getting this type of data set, or let me say you this type of data set. So what we are seeing, that a lot of values are very small, but few values we have which are larger. Okay, so this is skewed. So this is your skewed distribution. It can be positive skewed or it can be negative skewed. So you have very small value, and you can also have larger value, and division or multiplication of such kind of value can give you too much variability. And if we don't want such kind of variability, because it is a kind of noise it can produce, if we want very clear pattern, we can't get, because we may have a lot of noises because of that particular long tail. Okay, so what we do is, we transform our data set. So for example, if we are doing the log of our value, if we are log our value, then what will happen, that for example, your few values were near to zero point 0.1, zero point 0.2, and a few values were near to 1000. So if you are logging the value, all this value, then it will give you very short range. Right now the range is from 0.1 to 1000. But if you are doing log of this value, then it may be that you are just getting the value that is from 0 to 10. Then it will be easier for you to get some signature out of your variable. So that's how we are doing the transformation of our data set. Sometime we do the log of value, sometime we multiply with some multiplier, let's say for the with the 1000, something like that. So we have to sometime transform our data set so that the noise can be reduced. Then aggregation is, I told you, IMD. Okay, so again, I have Delhi, and we are dividing this Delhi into 16 grids. Okay, yeah. So IMD, that is the Indian Meteorological Department, if it is dividing your Delhi into 16 grids, but it may happen that some satellite may divide your Delhi in 16 into 4, 64 grids. How it can? Like this. So it may be that satellite may give you very finer resolution data set. If you are increasing your number of grids, then your data set will be very finer. For example, you can see the pixel of your camera, something like that. If you are zooming and still you are getting pixel, a lot of pixel, it means your image is finer resolution image. And if it is getting blur, if you are zooming, and then it is the cursor. So likewise, we may divide in Delhi into 16 grid, and even for the 64 grid and more grids. So more number of grid means more finer resolution that we are having of Delhi. Okay, so if IMD is giving me just 16 grids, satellite is giving me 64 grids, it means it is giving me the final resolution data set. And it may be that IMD is giving me the daily data set, but satellite is giving me, let's say, monthly data set only. It is giving monthly one value, and IMD is giving me daily one value. So for month it will give me 30 values. So there are some discrepancy. We have different resolution. So if number of grids are changed, then this is spatial resolution. If time, one is giving the daily and one is giving the monthly, so this is your temporal resolution. What I can say is that IMD and satellite having different spatial resolution and different temporal resolution. But if I want this both data set, then I have to match IMD resolution with satellite or satellite resolution with IMD. Either I can produce daily to monthly or monthly to daily. I have to have one, either it is daily or monthly. So that what we do is the aggregation. So for example, it is daily, but this is monthly. So what we will do is we will calculate the mean of your daily 30 values, and we will get the monthly data set. So both IMD and satellite will now have the monthly data set. So this is how what we do is the aggregation. Okay, so this we have to do for the climate data pre-processing. Parameterization, this is the part of climate model. To run the climate model, we have to do parameterization. That I can talk later, because right now it is not appropriate and you will not directly understand what you mean by parameterization right now. So I'm skipping this. Just keep in mind, this is the part of your climate model. Okay, so this is the slide that I got from NPTEL only. So data cleaning. So we are identifying and we are correcting the gaps and errors. Normalization, we are scaling data for uniformity. Transformation, apply log, power, or other transformation to stabilize variance. And we are aggregating. So this is resampling data to desired temporal resolution. I think now you can understand this slide in a better way. If you have doubt, you can let me know. Otherwise, we can go to the next question. Okay. The next question is, which method may produce artificial smoothing when used for missing data reconstruction? Again, I have five options: mean imputation, interpolation, replacement using nearby data, deleting the entire data set, and statistical smoothing. Again, I'm giving you the example of Delhi, and again, we have 16 or 20 grids. Let's say I'm dividing our Delhi into 20 grids, and if this grid doesn't have any value, if this grid is missing, we don't have temperature value for this grid. So what we have to do is we have to fill some value for that particular grid. But that filling value, so for example, the value here was 20, here let's say it was 22, and let's say here the temperature value was 25. So what we will do is, based on your nearby grids, we can take the average, or we can see the nearest one, and based on that, let's say if we are saying that the value for this is near to 22 or 23, but it may be that it is 30. The right value may be 30, because it may be a highly urban area. If it is highly urban area and the nearby are, let's say, forest grids, so based on nearby grids, we are saying we can fill the value as 22, but in real it may be 30 degrees Celsius. So this is something known as artificial smoothing. We are smoothing the value. We have peak, we should have 30 degrees Celsius, we should have peak of the value, but we are just smoothing. So it is something that uh, we, based on our nearby grids, we are feeling value like this, but in real it may be this value is this one and this one and like that. So what we are doing is we are smoothing the graph. So which method may introduce artificial smoothing when used for missing data reconstruction? Let me see the options that you gave me. A, B, C, E. Sanika gave me A, B, C, E. Yeah, this one is the right one. So the one is mean imputation. So mean imputation means whatever the mean of nearby grid you have, you are giving that value to the missing grid. So for example, as I told you, we have 20, 22, 25. So what we will do is 20 plus 22 plus 25 divide by 3, whatever value it will be, we will give it to the missing grid. Okay, so this is mean imputation, but it may be that this is not 22 or 23, it is 30. So this is how we are smoothing it. The second is interpolation. Interpolation is um, we have different type of interpolation. So if I'm taking the spline or nearest neighbor, so for example, I'm saying the nearest neighbor, whichever grid is very nearest to our missing grid, we are giving that value to that missing grid. So this is interpolation. Again, it may give you the artificial smoothing. Replacing using nearby data, just like interpolation. Again, this can give you the smoothing. We want the peak. There may be that particular grid can give you the peak, but you are just smoothing based on the mean value that we are taking from the nearby. Statistical smoothing, we have different method how we can fill the data, and statistically, that you will learn if you are going further for this remote sensing. So this can again smooth your data set. But what we want is we want actual, near to the actual value. So we again have different method how we can get accurate value. Again, this is a little complex, but yeah. Okay, the next question is, which are possible indicator of temporal inconsistency. Temporal means related to the time. Temporal inconsistency in climate record. Abrupt changes after instrument replacement, long-term sensor drift, seasonal gaps, irregular observation times, constant observation protocol throughout. How we will identify that there are some time related inconsistency? So again, I'm saying that this is my Delhi, and I'm again dividing my Delhi into some few grids. And this is temperature data set, let's say for the January. And again, I have Delhi, and again, I have temperature data set, but for the February. Okay. Then what I'm seeing is that, for example, for this grid, the temperature here is 15 for the same grid, but for the February, it is, let's say, 45-degree. So it means this value, either this 15 is wrong or this 45 is wrong, because there is the abrupt change. So how you will identify that there are some time related inconsistency in your climate record? So this is ABCD. Let me explain you again why. Abrupt changes after instrument replacement. So, for example, we had one instrument of a particular brand, and now this is outdated, and we bought new instrument, and we are now installing that new instrument at some study site. And what we will see, that instrument calculation may be different, and that's how there may be abrupt change in some climate variable. As I told you, we have, let's say, 15-degree temperature, but if we are installing a new instrument in the February and even in the January, for that particular grid only, we may have different value. And that different, if it is abrupt, if it is slow, then we can see, okay, this is seasonal change, and this is acceptable. But if it is abrupt change, if it is a sudden change, then we can say, okay, this may be due to the instrument replacement, or maybe due to different fault. So this is one, is the right one. Long term sensor drift. So what happen is, time to time we have to tune our sensor. In satellite, we have sensors. Sometime with the time, that sensor may start giving you the wrong value, we have to tune our wrong value. So this is long term sensor drift. Sensor may increase or decrease the value over the time, because of some algorithm that we may have in the sensor. Seasonal gaps. Again, this is showing us the temporal inconsistency. Irregular observation time. If we need hourly data set, or if we need daily data set, then we have to collect data hourly or daily. But if we are not collecting that data hourly or daily, if we are going to the field and we are collecting data after 10 days or after 15 days, then again this is irregular observation time, and this will also give you the temporal inconsistency that happen. So for example, we want to see at what time our flower is blooming. Okay, so for that, we have to go every day to the field to see at what temperature flower is blooming. But if we are not going every day, then what will happen? If we are going after 5 days or 10 days, we will see, okay, this is blooming, and we will note down when it is blooming. But it may be right or wrong, because we are not visiting that study site every day. And that's how this can give us the irregular observation times, and your research may be compromised. Constant observation protocol throughout, this can't give you the temporal inconsistency. This is what we want, actually. If you have any doubt, you can let me know. Otherwise, we can go to the next one. Okay. Next question is, which practices are useful when correcting climate data errors? Recalibration, statistical smoothing, replacement using reliable observation, verification after correction, keeping no record of correction. What we can do while we are correcting our climate data error? If we got some error in the climate data, then what should we do? Yeah. So I got value A, B, C, D. Yeah. So yeah, A, B, C, D are the right one. Recalibration. So have you seen that in the school time we used to calibrate our vernier caliper, or some physics related instrument. So what was that? So it was that we are tuning our tuning our instrument in such a way that it can give us in the millimeter or in micrometer. It can give us the milli or micrometer values, and that's why we used to tune our vernier caliper or a lot of instruments. So this is a recalibration. For example, sensor initially was giving you the right data, but with the time it needs some tuning. Okay, so it needs some recalibration, so that it can again start to give us the uh, right unit. So this is how we need the recalibrate. So if there is some climate error, then first what we will see, okay, if we are getting that data from satellite, then we need to recalibrate our sensors. Okay, so we will recalibrate it. Or if we are having some sensor in our study site also, for example, if it is a thermometer, or even we need to recalibrate our pH meter also, or thermal conductivity meters, so we need to recalibrate it. Second is, we need to do the statistical smoothing, as I told you. Sometime the climate data is like that. uh, each At that particular grid, the data was near to 15 degree, but at one day we got 40 degree. It may be due to extreme event, but we may also have doubt on this 40 degree. So we need to remove that 40 degree if it is wrong, and then we need to fill it with the nearby data set. So near to 15 or 19 degrees, so we are smoothing, but statistically with using some methods. Replacement using reliable observation. For example, satellite is giving us the wrong data, but because we also have data for that particular grid from observation also, so we can remove that satellite value, and we can fill that value with the observation. So this is replacement using reliable observation. Verification after correction. So when we are correcting it, again we have to verify that our data has been corrected or not. How we will verify? Using our observational data set. So we will compare and we will do the validation part. Keeping no record of correction, no, this is the wrong statement. So A, B, C, D are the right one. Okay, now you need to differentiate among two words, that are calibration and validation of climate model. Okay, now we are jumping to the climate models. uh, uh, Now, the thing is, there are two terminology, calibration and validation, and you have to tell me what's the difference between these two. Validation compares simulation with observation. Calibration may involve parameter adjustment. Validation requires changing every model parameter. Calibration may improve model performance. Validation assess how realistically the model performs. What is the difference between calibration and validation? Let me see the answers that you have given. What is the difference between calibration and validation? Calibration is tuning your model so that it can give you the correct value. Validation is whatever value you will get, you will compare it with the observation. This is the validation. So now can you tell me which are the right options? Calibration is tuning the model. Validation is comparing the output that the model gave with the observation. This is the validation. Okay, I got A, B, D, E. Yeah. So validation compares simulations with observation. So simulation is climate model output. We call it as a simulation because we are simulating our climate using some mathematical equations. That why uh, we call it the simulation of the climate models. So we compare simulation or the output of your climate model with the observation. That will be the validation. Calibration may involve parameter adjustment. Yes, that I will explain you right now. Calibration may improve model performance. Yeah, if we are tuning our parameters, then it can improve your performance, model performance. And then the validation assess how realistic the model perform. That I told you, we are comparing it with the observation data set. So this is how. Okay. uh, First what I do is I again show you something so that you can learn in a better way. Okay, so I have one model. um, so I have one model that is icon. This one, I have one model that is icon mpim. So this is earth system model. If I search here, let me show you icon esm model. So I have one Earth system model where each component of Earth is interacting with each other, and that's how uh, climate is simulated by that model with some equations, and it is giving us the climate data set. Okay, and that climate model can give us the data set even for the future. Okay, so this icon esm is comprehensive climate and earth system model that is developed by Max Planck Institute of Meteorology and partners. So if I'm using that model, let me show you what it is. It is not something materialistic thing, but this is equations that we have in the model. So Can you see, the model is nothing but it has a lot of lines, mathematical lines. The code is written, code is written, the shell scripting and a lot of Fortran, with the Fortran programming. The code is written in such a way that with the equations it can solve the equation of your atmosphere, and it is giving the value for a lot of variables. Okay, and that's how this is something that we have model. Okay, then what we do is, so I got the data set. So let's say I got temperature, relative humidity, precipitation, a lot of data set we will get from our climate model. Then we have to validate that. And again, I showed you, I can validate it using our observational data set, using a reanalysis data set. So what I'm using is, I'm using IMD or ERA5 or CMIP6 data set to compare whether my model is giving me right value or not. Okay, so I can use my climate model data set for future or not. So that's how we are using it. um, so now coming to again to our slides. So the thing is, we have climate models. So climate models are nothing, these are a lot of mathematical equations that we have that simulate our climate, and that's how it gives us a lot of climate variable values for the past and for the future. Okay, so this is your climate model. Then you have observational data set. As I told you, we have a lot of sensors that we install into our study site. Okay, then in the model we have lot of equations, right? We can improve these equation so that our model variable value can be improved. Okay, so if we are doing the improvement into that equations, then we will call it as the calibration. Okay, so after improving a lot of equation or its interaction with different component of the earth, so this is how we can improve the variable value. So this is calibration. But whatever value we will have after running this climate model, if we are comparing it with our observation data set, then this will be your validation. I don't know, like this may be complex for you, but just keep in mind that after getting the output, if we are comparing it with the observation, this is validation. But before getting the output, if we are correcting our model, then this will be your calibration. Okay. And the one word that I didn't tell you was the parameterization that we had in last question, something like that. So parameterization is, climate model can give you the data for the final resolution as well as for the coarser resolution. So let's say your observation is giving the data for the Delhi into 9 grids. Okay, but it may be that climate model is giving you the data for Delhi just in one grid. So there were some micro scale processes that were not resolved into this climate model. So that's why we have to put some value for that small scale processes, and that is something related to the parameterization. So we have to parameterize that small scale process so that we can have that, and then we can get the right value for the temperature or some variable. So that is parameterization. So but this is not right now important for you. Just the thing is calibration and validation, and you just need to know what is climate models. That's all. If you have any question, you can let me know. Otherwise, we can go to the next question. Now, is it clear that what do you mean by climate model? What is observational data set? What is reanalysis data set? What is satellite based data set? How, if we have some error, how we can fill that error, or how we can correct that error? If we have some gap in the data set, how we can fill that gap? So we learned about this, right? Okay. Now, okay, the climate model may have different type of climate model. We have global climate model. If the climate model is giving the data set for the world, for the global, it will be the global climate model. If that climate model is just giving the data set for particular region, let's say if it is giving data not for the world but for the India, then this will be a regional climate model. And why do we need regional climate model? If we are getting global climate model, then what is the need for this regional climate model? If we are simulating the climate for the world, then the resolution will be very coarse. Okay, but for the regional climate model, the resolution can be very finer. So that's why, after global climate model, we are relying on regional climate model so that we can get finer resolution data set for a particular region. Okay, so based on that information, you can tell me the answer: which features are generally associated with regional climate models? Focus on a limited regional domain, finer spatial detail than many global models, useful for regional climate assessment, no requirement for boundary information, can represent regional topography more explicitly. So, yeah, A, B, C, and E are the right. D is not the right one because we need the boundary condition. Let me explain you what is this boundary condition. But before that, you have to see this. So first, what we are doing is we are we are having the word and we are dividing that word into the grids, and then based on some equations we are calculating the climate related variable values for globally for each grid. But these grids are very coarser resolution grids, but we want information for a particular region, so we have to finer our resolution. So what we will do is, we will take information from global climate model and we will put that information on boundary. So let's say this is one grid of your global climate model, but putting that on the boundary, we can have the information for different grids now within that broader grid. So this is the regional climate model. And if we are getting the final resolution data set, then we can a lot of application is there to use it, right? So that's how we are using global climate model for the boundary layer so that we can simulate the climate in regional climate models. So that's how. Okay, so it is focusing on limited regional domain. As I already have explained, finer resolution, useful for regional climate model. It can represent regional topography more clearly. And then we need boundary information from global climate model. So no requirement is the wrong statement. Okay. Now we are coming to the earth system model. As I show you, we have a lot of like developed country have a lot of earth system model by which it is simulating the climate. As I told you, India also have one earth system model, that is IITM ESM. So this is one institute, Indian Institute of Tropical Meteorology, that we have in Pune, and this institute have this ESM, Earth System Model, that is IITM ESM. We have 100, or you can say 1,000 of Earth System model developed by different institutes. For example, Max Planck Institute have MPI ESM model and like that. So this Earth System model, what they do is, you have this Earth, right? So how, for example, you are burning something, okay, you are burning something, CO2 is released into the atmosphere, gases will interact with CO2, or radiation will interact with this, and based on that your temperature will be calculated. Okay, so this is how model do, based on how much burning is happening, how much nitrogen is getting recycled, how much respiration we are having, how much forest we have. Based on that, climate models or Earth System models calculate what will be the temperature, okay, what will be the relative humidity based on these processes. So if it is a Earth System model, it means one process interact with the another process, or you can say different processes may interact with together, and after that it simulates the climate. So this is the complex model where each processes are interacting with each other. Okay, so which processes may be represented within Earth System model? All possible processes can be represented within Earth System model. Atmospheric circulation, yes. Ocean heat transport, yes. Land surface processes, carbon cycle, cryospheric, each processes are interacting with each other, and then we are getting the simulated value. So this is how complex, and how uh, it is very complex to write in the equation, and even write in the code, to represent this, to represent different processes. It is very complex, but yeah, people are doing this. So Earth System model represent a lot of processes, and as below these, so these are all processes. Let me show you here. For example, here we have forest, and here we have atmosphere. So we have atmosphere biosphere interaction. Then a human may also give some response to the climate, and that's how we have human contribution. Then we have water cycle. So one variable is influencing the another variable, and based on that the temperature value is determined, right? So uh, so to incorporate all these processes in such a way that it can simulate our climate in a nice way, that what the Earth System model does, right? I think this is little complex, but this is what I can. You can tell me to explain more, then I can explain. But yeah, this is little complex to explain right now in a very short time. Okay. um from last 1 hour I'm talking about the resolution, I'm talking about the grids, right? How many grids we have, based on that we can say what resolution we have. So I think this is the nice question that you can solve very easily. Which statement about model grid resolution are correct? Small grid cell correspond to higher spatial resolution. Higher resolution can represent finer spatial structure. Higher resolution usually require greater computation. Coarser grid resolve more small scale features. Resolution can influence regional climate performance. Yeah. So I think I got correct response from Sanika. She gave me A, B, C, E. Yeah. So okay, as I told you, this is one region. Let's say we have 10-kilometer region. So We can represent this 10-kilometer region as one grid and as, let's say, multiple grids. Okay, so let's say Delhi is just 10-kilometer area, and if we are representing that 10-kilometer area with just one grid, or if we are representing that 10-kilometer area with 16 grids, so this will give us the more information. Okay, so it means smaller the grid cell, we will have high spatial resolution. Okay, higher resolution can represent finer spatial structure, because if we have just one grid, then one grid means we are getting the mean. But if we have 16 grid, then we can say, okay, here it may be water bodies, or here we may have agricultural area, here we may have forest area, and because of that each grid have different temperature value. But here we can't tell what kind of region it is and what exactly the value we may have for particular regions. So that's how, if we have higher resolution, that can represent finer spatial resolution, finer uh, after 100 meter, what it is, based on that what is the temperature, then another land cover we have, so based on that it can give you the finer spatial structure. Higher resolution usually require greater computation. Yeah, that's why if we have global climate models that have coarser resolution, why it is coarser resolution? Because we are taking the larger area. To make it finer, we need a lot of computation time, we need a lot of computational power. Okay, and if we don't have that, that's why we have to run our climate model on coarser resolution. If we have resources, then we can go with the finer resolution. So finer resolution will always require greater computation energy, computation power. Coarser grid resolve more small scale feature. No, your finer grid will resolve small scale features. Resolution can influence regional model performance, obviously. uh, if we will have finer, then finer will improve your regional model performance, uh, as comparison to the coarser one. um, when we are running our climate model, there may be a lot of sources of uncertainties or errors. What these can be: parameterization, incomplete process understanding, simplification of small scale processes, model structural differences, infinite computational power. So, as I told you, if we are running any model, or if we are simulating the climate using any climate models, we need to do the parameterization. As I told you, for example, if we have one process that can happen in 100 meter, but our resolution is 1 kilometer. So for that process, we have to put some value so that it can give that value while calculating the temperature. So this is parameterization. So giving that value for that processes can give you some error. So this is parameterization. Incomplete process understanding. As I told you, different processes in the climate are written in the code or written in the mathematical equation. So if we are not understanding that processes, how we can write correctly into the codes? And that's why if we have incomplete process understanding information, then our climate model will not give us the correct value. Simplification of small scale processes, this is known as parameterization. Okay, so this is again can give you the error. Model structural differences, different model may have different structural differences, and it can give you the error. So this is again the right information. If we will have this is not this can't give you the uncertainty, because more computational power we have, more finer we can simulate our climate model, and it can give us the better data set. So E is not the right option, so except E, all are the right answer. I think this is a last question that we can solve. Which model type is specifically designed around a simplified representation of Earth energy budget? So, how much radiation we are getting? So, most of the time, so sun is giving us the radiation. So, radiation means we are getting some energy from the sun. So, the unit is mostly watt per meter square. So, how much watt per meter square energy we are getting from the sun, and how much energy is getting out into the space from the earth? So, we try to balance it, and based on that, we can tell the temperature and all, because temperature is dependent on how much energy you have near to the surface. So, which one is that simplified model which is just based on your energy budget? Yeah. So, EBM is the one model, that is energy balance model, which just represent the simplified representation of energy. So this is very simplified. Reanalysis model I already have explained you. This is the combination of all the data set that we have, and then how we are blending this. So we are having some model to blend it. um, GCM is the global climate model, regional climate model. These are the complex model as comparison to the EBM, and the most complex model is the ESM, that is the earth system model, where all components are interacting with each other, and then we are writing the code in such a way that we can simulate the climate. Okay. So which data set or observation may help evaluate climate model performance? Each type of observation, whatever observation data we have, that all data set can help us to evaluate the climate model observation. So either it is historical climate record, or we have satellite observation, or ground based, or reanalysis, or ocean observation. We just need the observation so that we can compare our observation with the climate model data set, so we can see the performance, whether our climate model is giving us the right data set or not. Okay. So this we will do from next session. So I think this is where I should stop, because it is already we already have crossed 8. So thank you so much. If you have any question, you can let me know. If you have any suggestion or query, you can just let me know. If you want some improvement in this session from next week, you can write in the chat box. Otherwise, this is your dinner time. Sorry for taking more time. So thank you so much. Okay, I need to give you the link also. So I'm sharing the link.